Hello everyone. In this lecture, we will learn how delete operation works in red-black tree using practical examples on Java. As an overview of this lecture, we will look at definition of successor and predecessor nodes in tree structure, deletion cases without balancing, deletion cases at balancing phase, and finish with the practical example. Predecessor of a node of value x is a node of the tree whose value is the greatest that is less than x. The successor of a node of value x is the node of the tree whose value is the least that is greater than x. Let us clear this statement with an example using the given red-black tree. So let's pick our x node as node 150. Predecessor of value x is the greatest that is less than x. So when we look at the connected nodes of node 150, which connected node is the greatest that is less than node 150? It is node 148. It is less and it is the greatest. So the next definition is the successor node. Successor node is a node of the tree whose value is the least that is greater than x. We know that the right subtree of node 150 will contain only the nodes that are greater than node 150. If we get the right child of node 150, the left of its right child will contain the values that the one could possibly be the least. So the right answer here is 170. If the right child of node 150 wouldn't contain a left child, then it would be node with a key value of 200. This is how we can determine a predecessor or a successor node in red-black tree. At the next slide, we will have a look at deletion cases in red-black tree. Deletion cases can be expressed in many forms. The way shown here is the way that I find the most convenient. So in this way, I split deletion cases into two groups. In one, we have cases that are cases with no balancing applied, and at the second, we have the cases when balancing is required. Cases without balancing are as follows. Let's assume that Z is node to be deleted in our red-black tree. Then, in case 1, if node Z has no left child, we remove Z and put its right child instead of it. In case 2, if node Z has no right child, then we remove Z and put its left child instead. In case 3, if Z has 2 children and its successor is its right child, then we remove Z and put its successor instead. And also make Z's left child as a successor's left child. In case 4, if Z has 2 children and its successor is not its child, then we put the successor's right child instead of it and remove Z and put its successor instead of Z. The second group is balancing, where balancing is required for the red-black tree after deletion. Whether red-black tree needs balancing or not can be determined by knowing the term called extra black node. If Z has extra black, then we balance the tree, and if not, that means we don't have and we do not violate the red-black tree property. So this said, let's have a look at the cases of balancing in red-black tree. If left subtree is unbalanced and node Z has extra black, then we fix the X depending on cases. X is used to determine the node that will be involved at the transplanting or and rotating process of the red-black tree. So this said, let's have a look at case 1. In case 1, if X sibling is red, then we switch the colors between sibling and X's parent and rotate parent to the left. In case 2, if X's sibling and its children are black, then we move X to X parent and change the color of sibling. In case 3, if X's sibling is black with left child red and right child black, then we switch colors between sibling and sibling's left child and right rotate the sibling. In case 4, if X's sibling is black with right child red, then we make sibling color equal to X's parent color, make X's parent color black, make sibling's right child black, and left rotate X's parent. And additionally, if none of above cases exists, then we color X back to black and finish the balancing. Before going to next slide, to see the cases mentioned here, I would like to remind you that in balancing, if right subtree is unbalanced rather than left subtree, we basically do the same thing, but with only difference. We basically change the direction of the rotation and the nodes that should be colored. So let's assume we have unbalancing at the right subtree and we are satisfying case 1 where X's sibling is red. Then we would still switch colors between sibling and X's parent, but this time instead of rotating X's parent to left, we would rotate it to the right because we have right subtree unbalanced. That's the reason. So you should keep this in mind. The same things, just the directions do change. So same for case 3. Let's give example from case 3 as well. We would switch color between sibling, but instead of switching with its left child, we would switch with the right child and left rotate the sibling instead of rotating it right. So I suppose you caught the idea. Before further ado, let's jump into implementation of delete operation in red-black tree. In this and upcoming slides, we will try to testify most of cases given to delete a node in red-black tree. Every deletion starts with root node. So our input for the node variable is root. For convenience, of course, you may go on and create additional method to call the root node and pass the key value you want to delete. So as our first node, let's delete node with key value of 135. At the next 2 lines, we create 3 local variables where we can track node to be deleted, which is Z, extra Y node to know if we have extra black for balancing, and X node for transplanting or and rotating the node required for balancing. Just like in any binary search tree implementation, from line number 5 to line number 14, we are going to locate our node to be deleted. So our node is T-null. We stop executing while loop. At line number 15, we are basically throwing error message if key to be deleted doesn't exist and return from method to avoid unnecessary executions, which also could break our red-black tree. So we skip this if statement and set our Y value to store original color information to determine whether we have black node or red node after deletion. Rest of algorithm from this point on relies on the cases we have defined in previous slide. First, if statement checks the case 1. If Z has no left child, and yeah, our property fits to case 1, Z node doesn't have a left child, so we need to remove Z and put its right child instead of it. We set X as the right child of Z and do transplantation. So next, let's see how our transplanting method works with given inputs. At first if statement of rbtransplant method, we are checking if the node we deleted is the root node, because if it would be root node, then it wouldn't have a parent. Well, in our case it's not, so we skip the statement and get to the next statement where we determine if node to be deleted is at the right or at the left subtree of the parent node. This is crucial because this way we know what the parent should point now. This is also the actual transplanting and removing process of our desired node. So now we change the Z's parent's left pointer to point Z's right pointer. We skip the else statement since we have already executed an else if previously and update the new parent of Z's right pointer. If you look at our red-black tree visual closely now, you will notice that we actually satisfied case 1. Z is theoretically removed and now Z's parent is pointing Z's right pointer, which means we put its right child instead of Z. Well, I say it theoretically because Z is still in the memory at this current state. Well, no worries, it will eventually be erased after our delete operation is over. At line number 24, we skip until line number 43 because if statement was executed, therefore rest of else body will be skipped. At line number 43, we check the extra color information because if you remember from previous slide, we make correction if we have extra black assigned on node Z. We kept that information in Y original color variable, so we can check it now. If you look at Y original color variable, its color is black, so we need balancing in our red-black tree. We pass X node here as it is the successor node now that holds that old location. We create sibling node at the next line to determine the sibling node of our X value. Well, if you look at the while loop condition, we do not need to do actual balancing because node 135's right child, which is also our X node, is a red node. Therefore, the only thing we need to do is to recolor it back to black, which will be enough to hold valid red black tree structure. So it's none of the cases, and we color X back to black and finish. So next we are going to delete node with key value of 78. Same process as previous one, so I will get through the code example and start explaining when we get to cases. So here we don't have the first case because our Z has left child. At the next else if check though, we satisfy case 2 where our Z doesn't have a right child. Similar to case 1, we remove Z, but this time put its left child instead of it. The node we are deleting is not the root node, and transplantation should be at the right subtree of Z's parent. We change the pointer of Z's parent to point the left child of Z, and update the new parent of Z's left child. We have extra black. Again, none of cases at the balancing phase, so we color X back to black and finish. Next key value is 180. I will slowly go through code again until we get to cases. So Z has left child, so we skip the first case. And at the next one, we try to find its successor node, because determination of which remaining cases are applied will depend on the successor node's location. So as we remember, successor node is a node that is greater than the Z that holds the least value. To find it, we have a method called minimum that requires input. Our input here is Z's right, because we know that Z's right will be greater than Z, and finding minimum from that node will give us the actual successor. In the minimum method, we know that if node with key value 200 had left node, it would go through that left pointer until there's no more left node to look for. But in our case, it is null. So this method will be returning node 200 as the successor node of node Z. After executing minimum method, we get to the next line where we basically set our X node to be located at the right pointer of node Y. At the next line, we check if we have case 3. Case 3 defines that if Z has 2 children and if successor is its right child, then we do the arrangements defined. We can check if Z's right child is the successor of Z in a couple of ways. The way I used here basically checks if node Y's parent is Z. If it is Z, then Z's successor is its right child, because we have set node Y as the successor of node Z at line number 28. So yes, we satisfy case 3, where Z has 2 children and its successor is its right child. This means we need to remove Z and put its successor instead of node Z and make Z's left child as the successor's left child. So let's see it in action. We this time take Z input and Y input for transplant method. Change the pointer of Z's parent to point Z's successor, and update the successor's new parent. One part is over. We did remove Z and put its successor instead. Now we need to make Z's left child as the successor's left child. We basically update left pointer of Y to be the Z's left pointer and update the Y's left pointer's parent to be Y node, which was set as Z node previously. And also, we take the color of Z since Y took now place of Z and finish the case 3. We have extra black, so we get to the balance delete method by passing the X variable. At balance delete method, again no cases are met, so we color X back to black and finish the deletion. Until this point, I know that we didn't testify the cases for balancing, But don't worry, in this last deletion, we will cover at least 3 cases of deletion for balancing. So at this last deletion, let us delete node with key value of 100. It is also our root node. I'll go through the code example until we reach the point where we need to check deletion cases without balancing. At line number 21, our Z node is 100 and its left is not null, so we skip case 1. We also skip case 2 because right pointer of node 100 is also not null. At line number 27, we are going to find our successor node and set our Y and Z to required locations for transplanting. At line number 31, we check case 3. If case 3 would be true, our successor node had to be a right pointer of node 100, but it's not. Successor node is node 136 and it is not the right child of node 100. So we skip to the case 4. Well, case 4 is the only case that left. Node Z has 2 children and its successor is not its right child. This means we need to put successor's right child instead of successor and remove Z and put the successor instead of it. Let's see it in action. At the else if statement, we basically satisfy the first rule, update the right pointer of successor's parent and finish. The next rule is to remove Z and put its successor instead of it. So logically, we need to get Y to point its right pointer to the Z's right pointer and change the parent of the pointed node to point at new parent. At line number 38, we now need to change the root node because Y should be the new root. This is the importance of first if statement in RB transparent method. If the input has no parent, then the successor is the new root. Our Z is root because it has no parent, so we assign Y as our new root and update its parent to null to complete root property on node Y. We have updated right pointer of successor. Next, we need to update the left pointer. We basically do it at the next line at line number 39. And update the new right pointer's parent to be pointing at Y. Y now should get the color of Z and we get to the balancing method. This is how our red-black tree would look like after executing the delete method. At the balance delete method, we create sibling node and put it as sibling of successor. In case 1, if X sibling is red, we switch color between sibling and X parent and left rotate X's parent. We have node X here as an input variable in left rotate. It's different X2 than the X variable we have, so I will assign it as X2 instead of X because they are different. In line number 12, we create Y node to be assigned the right pointer of node X2, which is the parent of our node X, and change its right pointer to point at Y's left pointer. Well, this is actual left rotation that we know from AVL tree. So if you are familiar with AVL tree, you should know why we are having this kind of strategy when we are left rotating specific node. At the next line, we check if Y's left pointer is not null, because if not, we need to update the new parent of Y's left pointer. At the next line, we update Y's parent to be X2's parent because at the coming steps, X2's parent's left pointer will be pointing at node Y. At this if statement, X2 is not the root node, so we skip. And at the next else if, we check if X2 is the left pointer of its parent. Because if it is so, then we will know that it should now point at node Y to apply process of left rotation. At the next line, we change the left pointer of Y to point at X2 and complete our rotation by updating the new parent of X2. After executing left rotation, we update the sibling's location because it was rotated in line number 10. Next, we check if we satisfy case 2. Well, no, because sibling's left pointer is red. So we get to else statement and check if its right pointer is black. If it is so, then we conduct case 3. And yes, it is black, and this way we know that sibling's left pointer is red and its right pointer is black. Because if it would be otherwise, then we would be skipping this else statement where first if statement would return true. At case 3, we should switch colors between sibling and sibling's left child and then right rotate the sibling. After right rotating the sibling, we are now going to update the new sibling of node X. So next, case 4. If X's sibling is black with right child red, then we do the following arrangements described at the left bottom of this slide. Sibling color becomes as X's parent color, we color X's parent to black, make sibling's right child black, and left rotate the X's parent. I will go through the code example slowly, and we will finish with the case 4. At line number 32, we set X to root because of rotation methods. We could be rotating the actual root after deletion of some specific node. So that is why, after fourth case is executed, we set X to root and make sure that it is black to keep black root property of red-black tree. In this lecture, we learned how red-black tree deletion works in data structures. Before saying goodbye, I would like to remind you that you may encounter different deletion cases and definitions plus implementations of red-black tree delete operation. This is common occurrence as it is a complex algorithm and can be managed using multiple approaches. For example, there are some implementations that rely on predecessor node instead of successor node. Some deals with extra black node totally different than the one we have seen here. At the end of the day, knowing the methodology of how red-black tree is implemented is enough to apply your solution for all operations taught in the sequential lectures. I hope this was an informative lecture and you learned how red-black tree works in data structures. Thank you for watching. Until next time.